So I'm Andy Fundinger. I've been a Python developer since Python 2.4. The first Python books I got said Python 2.2, newly revised for Python 2.3. And they had a few pages in the back that said, when Python 2.4 gets here, this is what you're going to get. And all the exciting things that were coming in Python 2.4, which is what I was running. Everything we're doing today is Python 3 with some notes about when we actually got them. I work for Bloomberg. Bloomberg sells financial data and analysis. We have about 5,000 developers. We have over 5,000 developers, 2,000 of them focused on Python, mostly in New York, London, some in San Francisco, and smaller offices throughout the world. This talk is about decorators. And it's about the fact that when we go to talk about decorators, it's hard to get them into categories, and we historically have not done that. The idea is with a common terminology, we can start to discuss more easily our decorators and our uses and the problems there in sort of like design patterns. I feel it's a little bit different. This talk is targeted at intermediate developers. People who can write decorators, but maybe aren't sure when or why you might want to do that. And architects who might want to work across teams to implement or manage their design. We're going to do a brief review of decorator syntax and implementation, but this is not intended to teach how to write decorators, just to review it, so if you haven't seen it recently or haven't thought about it, you're fresh on it for the rest of the talk. Just a note, of course, like anything, any decorator can be replaced by taking the code that's in the decorator and pasting it enough places throughout your application. Decorators are all about taking this code and allowing it to be reused and factored out of the functions that are being decorated. Generally, the decorators are inserting a section of code which is of flat-out arbitrary complexity into a single line, and that outline is actually above the function, above the def, so you're not even seeing it if you read the code casually. Your debugger is often skipping over it, and so are your eyes, for better or for worse. The decorators started in Python 2.2, and they started with static method, class method, and property. We used to write them like this. And this is still all they're really doing. But in 2.4, the @ sign was added as syntactic sugar that we tend to know today that does exactly the same thing. We can, of course, write our own. All it is a function that takes a function and returns presumably some sort of callable. Here's one that takes whatever function it's decorating and returns a function that always returns none. By Python 2.6, we could decorate classes. So we can take that nullet decorator and decorate this class. And now anytime you try to construct an instance of this class, you get none. Maybe not something you would want to do, but syntactically it's allowed. Where we usually start having some trouble on our implementations around decorators is when we want to use decorators with arguments. So we'll take a quick look at that. Here's a decorator with an argument. The trick to this is that it's not doing anything at all. All Python is saying is, oh, I see a function here, I'm going to run it, and I'm going to expect that that returns a decorator. And I'm going to expect that that decorator will then take a function, and that function will wrap in exactly the way as any other decorator. So here's one of those. Multarg takes an argument of some number to multiply by. It returns the actual decorator, which takes an actual function. That function returns a wrapper that calls the function that it's given. multiplying by mult, and off it all goes. As an example, we've decorated print x with mult arg3. Normally print x would just print x. If we do print x1, having decorated it, we get 3. If we do print x of hello, we get hello, 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 because after all, we can multiply strings. Notice this is 2 closures, one for the argument, mult, and another one for the function, func. Normally, for some reason, which I personally am not quite sure I understand, we do tend to write our decorators as closures. There's not a particular benefit to this. We can write them as classes. It just has to return a callable. So here's an example of doing that. Class traceIt captures the function in init, stores it in a class, in an instance variable, and then call. When it's called, calls that function. So we decorate traceIt around this rand function, and then when we call it, we print out the arguments that were called, and off we go. Okay, enough of that. Let's move on to the actual taxonomy. We'll start with A because I put these in alphabetical order. The argument changing decorators are decorators that add or remove an argument when the function is called, or maybe they just change the value or type of an argument at call time. The problem is, if you go look at the code that you have decorated and then go, I'm going to call that, it won't work. If you're trying to call it for a test, you're going to have to do something to set up the decorator so that the code can actually be called. So we'll take an example of this, as we will for each of these. The click library is a wonderful library. We use it quite a bit. Click command and click option, you put them together. And what this will do is cause click to go to sysargv and get --n from the command line and pass that in to your function. The signature of the function has now changed to pass no arguments. Click will get them for you. If you try to pass the argument, it will not work. We can write our own. Here's one. Most functions do not know what their own name is. It would take some stack manipulation to figure that out, or we can have a decorator that does that. So here's a function with name decorator. The wrapper says, okay, I'm going to take the function name and I'm going to make it the first argument to the function. Why? I don't know. So we'll decorate this self-aware function with it. Doesn't do much. It just prints its name and the other argument that's given. You would think that you call this with 2 arguments, but when we actually call self-aware here with 1 argument, it prints out self-aware here, and that's the right way to call it. There's a variation of this which bothers me a lot because it messes up my alphabetical order. But other than that, it's great. The return value decorators run the function perfectly normally, but only mess with the output. So I pulled an example from Turbo Gears. They have one add expose, which will take a parameter JSON and say whatever this thing returns, make it the JSON version. And here it is. It's relatively simple. Pass back a dictionary, and Turbo Gears will take care of that for you. They only alter the output, so it's a little bit less problems with that, but still some. Again, we can write our own. I decided to mess with function name again. This is a composable result decorator. It takes whatever's returned and turns it into a dictionary keyed by the name of the function. So if we take process 1 and process 2 and decorate them both with composable result, then we can take those results and update them both into a dictionary. And we'll get a combined dictionary that has all the results. So let's move on to something completely different. Here's a binding decorator. The binding decorators implement the descriptor protocol, and they change how binding works in Python, which is itself very, very fun. The standard library provides our best examples of this with static method, class method, and property, but they aren't the only ones. The problems here are we're kind of used to our methods working the way they work, and this just changed that. So we get a new language pattern that maybe just came in from another language, something like lazy execution, something that's not how I thought my function was going to work. We might get a new exception that we didn't think could happen or happened at a different time. Here's one. SQL Alchemy has a thing called a hybrid property. It runs a different set of code on the instance in the class. So on the instance here for radius, it just does the math and calculates the radius. On the class, it generates a SQL statement so that it can be used in a query. Again, we can write our own. Let's disable a feature in Python. Normally, we can do things with our instance methods. We're used to how those work. If we want, we can get the unbound one, but let's make true instance methods in Python. We'll not have any of this getting at the class version of that. So this is an instance method decorator. It's a descriptor. And if you try to get it from the class, we'll have none of that. So here's good class. It's a good class. We'll have two methods. They're exactly the same except for this decorator. Simple method, which is decorated, and normal method that's not. If we call them on instances, they both work exactly the same. Normally, we can get the unbound version of this function, and it's just a function in Python 3 or an unbound method in Python 2. However, if we want to go and get the simple one, we have disallowed that. It is now a type error. That might, in a very limited case, be useful just like that, but in a more stretched case, you get into something like SQL Alchemy, where you are saying this is a behavior. Another, if not the most common kind of decorators are our control flow decorators. Our control flow decorators control whether a function will be called and how many times. The problem is now you wrote code to call a function and you don't even know if that function got called. So you might write code that says, I don't know, hits PayPal and sends some money, and maybe it gets called 2 or 3 times, you know, just because the decorator did that. This is one that you probably try and retry a few times. If you haven't tried it yet, I suggest you retry it again. Retry. Great little decorator. Straight from their documentation, throw it on something that occasionally breaks, and it'll try it again. If you do go to use this, they have a whole lot of options. You can have it do like exponential back off, try it a maximum number of this times only if you have these exceptions. Probably doing it exactly like this is not ideal for your case. Of course, we can write our own. This one's even worse because it does it infinitely. But it exposes, you know, exactly the sort of thing you're looking at. We'll have an infinite retry while true, as long as we get a runtime error. Just go ahead and run that function again. And here's a function, anytime it comes up with a negative number. Yeah, sure. Just call it again until we get a positive number. That's a great way to get a positive number from 1 to 10. The descriptive decorators are actually the ones that caused this talk to come into being because someone told me they didn't exist. They told me that all decorators changed the data going through them. And I said, well, what about the descriptive decorators? They either add the decorated object to some sort of collection or maybe change some metadata property on the function for the purpose of documentation, patching, plugins. The problem is they did something, but they changed nothing. So it's unclear how the dispatching is going to be done. And if it didn't work, it's unclear what didn't work because you put the decorator there. And if you decide you want to tweak that registration, the decorator didn't give you a clear idea from that point. You just put the decorator there. PyTest marks says this. Look, I marked it as a web test. It's now a web test. If I run pytest-m web test, it marks everything running as a web test. It collects all 4 tests, but there's only one dot there because it only found one that's a web test and it ran that. It's good. I recommend using these marks if you haven't tried them, but the mechanism behind it, as long as when it doesn't work, is unclear. There's another one, which you may use a lot. Routing via decorators. When you add a Flask route, you add a app route decorator, and it takes your function and adds it to a routing table. Doesn't change your function. If you ever write unit tests that hit this function directly, you can call it. It's the same function as it ever was, but a whole different set of machinery is now plugged into this function. This is the example I wrote in that discussion about how these didn't exist. This is a QA list decorator, made very quickly to show the point, but here's a global list of things that need to be QA'd. You'll notice the decorator here is returning exactly the function it was given, but it grabbed the name of the function and put it on the list. So the new code and the refactored code has been marked. It needs to be QA'd before release. The well-trusted code, we're good. And if we look at it, our list has been maintained. Somebody please take this mechanism and make a library out of it. I want to use it. Here's one. I'd like to know, as I go through this, how many people have actually encountered these in the wild before I show the open source example. The execution decorator reads your method or class or your code, which it may then reinterpret the source code to basically not be Python. The problems here are just plain infinite because you just changed the source code to not be Python anymore. This truly means the code you've wrote is changed by the decorator to some other code that is then executed. So it might just be analyzed for dependencies. It might have objects in the AST swapped out, injected, or removed. It might be recompiled by different rules. Number does this. Number.jit. This is right from their documentation, as the open source examples have been. You throw this on a function, and if you follow the rules of number, the function is faster. If you didn't follow the rules of number, it will crash. I'm not sure whether that's a runtime crash or a compile time crash, but it will crash. We can write our own of this. I don't recommend it, ever. But here's one. We'll take the function. We'll grab the source code. We'll chop it into lines. We don't need line 0 because that's at replacer. We need line 1. That's the name of the function. We'll take the rest of the lines. We'll run a basic search and replace on that. Then we'll exec it. And we'll take the globals, we'll pull that same function name out of the globals, and that's a new function that we made. Gosh, it's good. All we have to do is return a function. So here's our sample function. If we run it normally with 1 and 4, we get 10. But if we replace b with b star b and run it, we get 26. If we replace a with a star 3 and run it, we get 14, but we also turn sample into a star 3 MPLE. In the not recommended case you ever write one of these, there are other tools available, like manipulating the bytecode or the AST. Still to be avoided, but. Now there's another category way down the end, and I have problems with these two. These are the wrapping decorators. Supposedly these do nothing. They just run some code around the function call, and they don't even count as a descriptive decorator. They don't affect the function at all. And I think they should generally be replaced with context managers. They do so little that my greatest fear is that they throw an exception and then they become a control flow decorator you didn't expect. They also force your code, once you've decided you're going to use this, you wind up forcing your code to have a function here just so I can use the decorator that I wrote. But I have found one of them that does seem to fit very logically. I can see why the time call decorator is probably good to be a decorator, and I can see why it shouldn't be changing anything from the profile hooks library. So they do exist, and obviously I don't feel compelled to show how to write one because you just don't do anything. So they do exist, and I can name them. So in conclusion, here's the 5 main kinds that I've named so far, plus return value and wrapping. And here's some other examples beyond the ones on the slide. Argument changing, we have parameterized from PyTest also. Flask templated has a argument changing decorator. Binding, there's a new library called Variance. It's kind of fun. Does some tricks with binding. Pyramid also does one. Control flow, LRU cache in the standard library, or anything doing memoization. The inline callbacks from Twisted is good. The descriptive decorator, there's a set as test in NumPy. Cython obviously has something very similar to Numba, though you do have to already be running Cython rather than Python there. There's also a few that I'm looking at. I'm just not sure whether they're common enough to be worth naming. You can take 2 of these and make them in the same decorator. I would call that a hybrid decorator, but I'm not sure anybody cares. There's an old pattern from Python 2 where you could use the add-apply function, and you could write some code that only runs once and then becomes a constant value on the class. I'm not sure I can find places where we're doing that significantly anymore. You could write it still. Again, I'm not sure that's worth naming. And I'm very much looking for others or for things that don't fit into these, or for anything that you feel these need to be divided or renamed or added to. So I'd like to hear very much about those through the rest of the conference. Thank you very much.